Hello. In this video we're going to look at the stresses that occur at 2 points in a cantilever beam subjected to an axial load P, a bending force F, and an applied torque T. The length of our cantilever beam is L, and the diameter of our cantilever beam is a constant, big D. I typically will look at stress elements at the top of the cantilever beam and also at the side of the cantilever beam, because based on this loading, that's where the maximum stresses will occur. Before I start a problem, if it's been a while since I've done one, or I need to remind myself of the equations that can occur for the stresses, I will simply write the stress equations down. In this case, I can have a sigma equals an MC over an I for bending stress. I could have a sigma equals a P over an A for an axial stress. I could possibly have a tau equals a TC over J based on the torque, and I can have a tau is equal to VQ over IT. Given that I am going to be looking at the stresses back here at the wall, and the force, the transverse force is applied out here at a distance L, there is no possibility that I can have a tau equals P over A stress, because the force does not occur at the point where I'm trying to determine the stresses. So to define the stress elements that I'll look at a little more clearly, I will draw the cross-section of the beam as if I were looking into the beam from this direction. In this case, I will be looking at an element that occurs right at the very top of the beam and an element B that occurs here at the side of the beam. These are infinitesimally small elements, but I will draw them as finite-sized elements to allow me to clearly describe the stresses. So if I were to draw these elements back here on my structure, I would have element A wrapping over the top of the beam, and I would have element B here on the side of the beam. I've determined the stresses that occur here. I've defined the locations I want to know the stresses, and I'm ready to start to solve the problem. The first thing that I do is draw a free body diagram of the structure. In this case, I will draw this in a two-dimensional drawing so that it's more clearly easy to see the stresses that occur, or the reaction loads. So I have a transverse load F, I have an axial load P, and I have a torque T. If I want to use arrows, double arrows to describe the torque, I would simply draw them in this direction, put my double arrows in the direction of my thumb based on the applied torque, and my double arrows would be going in that direction with a magnitude T. Now I apply summation of forces and moments. Summation of forces has to equal 0, and in this case it's very trivial to apply and determine the reaction loads. This would be my X direction based on my definition of X, Y, and Z up here. Y would be going vertical and Z would be coming out of the plane. Summation of forces in X has to equal 0, and that will simply tell me that I have a P going in the negative X direction, and so I consider that done. Summation of forces in Y has to equal 0, and that's simply going to tell me that I have to have a force F in the vertical positive Y direction at the point where I'm determining the stresses or the reactions. Summation of forces in Z is done because I have no Z applied forces, so I'll have no reaction forces in the Z direction. Now I do my summation of moments equation, and I know that the summation of moments also has to equal 0. I will have a reaction moment because this joint, a cantilever beam, can carry a reaction moment. So it is possible that I have a moment at the point where I'm trying to determine the stresses. I move along my beam and I look for any applied torques and points where forces are applied. So as I move along my beam, I hit an applied torque. This torque is applied in the positive I direction or X direction, and I'll denote that as the unit vector I. I then come to this point where I hit my forces, and so I will have a plus an R cross F, which represents the moment due to the forces at this point. All of this will be equal to 0. Now I need to determine what exists in my cross product R cross F. So R cross F will be equal to I, J, K unit vectors. In the X direction, to get to the point of interest, I go L. So my point of interest is at the wall. To get to where the forces are applied, I go a distance L in the X direction. I don't do anything in the Y direction. I don't move at all. So I'll have a 0. The same in the K. I don't move in the K direction or along the Z axis, and so I'll also have a 0 there. Now I simply write down the forces that occur at this point. In the X direction, I have a load P, and I need to note that it is a positive P that occurs in this direction. I have an F in the negative Y direction, so I will have a minus F in the Y direction. I don't have any forces in the Z direction. Now I need to evaluate this cross product. To evaluate this cross product, I have 0 plus 0 plus a minus FLK minus the quantity, now 0 plus 0 plus 0. So my R cross F reduces to minus FLK. Now this could have been done in our head as well, but in more difficult problems, this cross product approach will save you from making a lot of mistakes. My moment then, my moment expression can be written as hauling the T to the other side is equal to a minus T in the I direction. My minus FLK hauled to the other side becomes a plus FL in the K direction. Now I can draw the moment that occurs back at the wall on my free body diagram. I'm going to have a minus T, and I can draw that using the double arrow approach as a minus T would be going in this direction, where my thumb would be in the negative X or the I direction, and so my double arrows would be going like that with a magnitude of T. My FLK will be about the Z axis, and it will be a positive, so I put my thumb in the positive direction and draw my double arrows, and I get double arrows that would look like this and would be in the positive z direction. Now I'm ready to draw the stresses that act on my stress element. Doing that, I'm going to keep my free body diagram in view and remember that I'm looking for the stresses that occur on an element A and an element B. So I will look at the stresses on element A first. I'll draw element A as a 2D stress element because this system happens to be in plane stress. Now I simply look at my reaction loads, my forces and moments, and ask myself, what does each force and what does each moment do to element A? And here are my four choices of what that particular load can do. So starting off with my P load, or my axial load, it's not a moment, so there's no way it can do MC over I. It's not a torque, so it can't do TC over J. And it's a normal force. It's not a shear force, so it can't be a V. So there's no way that this normal load P, which is perpendicular to the cut plane of interest, can be anything but sigma equals P over A. So I'll now come and draw sigma equals P over A on my stress element. And it's acting in tension. P's trying to pull my element apart like this. Now I look at my F force, and my F force is coming up along my element in this direction. The F is not an M. It's now not a normal force. It's not a torque. It could be a VQ over IT shear force because it certainly is a shear force. It's a shear acting in the plane. But I need to remember the stress profile for the shear. And I need to remember that a transverse shear, where the shear force passes in that plane, Q will be equal to 0, and I will be looking at a stress-free surface. And so force F will not do VQ over IT because that arrow would pierce right through F. It would shoot, or excuse me, through A. It would shoot right through element A. It wouldn't be going up along any of these sides of element A. It would shoot right through it. So it does not do a shear stress. Now I look at my reaction torque, and my reaction torque is going in this direction. My reaction torque is not a moment, it's not a P, it's not a V, so my only option is a TC over J, and indeed it does do a TC over J stress. And on this side of A, if I look at A as occurring right here, that shear stress is coming up on this side of A, so it will be coming up on that side of element A, and the magnitude of that stress will be TC over J. So tau is equal to TC over J. Now my last reaction load to consider is this moment FL about the z-axis. And this moment is trying to bend my beam. It's trying to bend my beam up. The reaction is trying to bend it up. And so if I draw this reaction a little more carefully and draw it in terms of a circular vector on the cut face, this moment will be coming out of the top and into the bottom. So that vector, my FL reaction, is coming out of the top and into the bottom. Coming out of the top is going to pull on element A and put it in tension. And that will be a tensile bending stress where sigma is equal to MC over I. And in this particular case, my moment is given by FL, so I will have FL C over I. That completes the stresses that occur on element A. Now I'm ready to look at the stresses that occur on element B. So drawing my element B, B is going to act on this side of my cantilever beam. So essentially I could draw B acting right here. And I'm going to label the stresses that act on element B. P, again, is not an M. T, it's not a shear force because it's acting perpendicular to the face. So it's a normal load. The only option is sigma equals P over A. And again, it's in tension because P on the cut face is pulling in this direction. The load F in the vertical direction now is parallel to this face here at B. So it's going to act right along that. It's parallel to that face, and that will cause a shear due to bending. So this would be a tau is equal to a VQ over IT. In this case, we know that it's a cylindrical geometry, so VQ over IT reduces to 4/3 V over A. And we recall that V is given by F, so we have 4F all over 3A, where A is the cross-sectional area. We've now considered the 2 point loads in my geometry, and we're ready to look at the torque and the bending moment. The torque, again, is going to try to twist B. It's twisting the shaft, so we know that it's not a moment, but that it is a torque. And again, on the cut face, it's going to twist that up. So on the cut face, we'll be going up in the same direction, and we have a tau is equal to TC over J. The last load component to look at is this bending moment, and we realize that this bending moment is trying to twist my beam up, bend my beam up, I should say, and B occurs at the centroid of that twist, and so it occurs at the neutral axis, and this bending moment FL will not cause any stress due to bending at location B because it's at the neutral axis. I hope this has helped you better understand combined loadings and determining the stresses at particular points due to combined loadings. Thank you for watching.